post that my colleague wrote, which you can find on Distill's website, or this bit.ly/distillml. What is Distill Networks? We block malicious web bots. So our product in between clients making HTTP requests and our customers' origin servers, and we filter out bad traffic. So web scraping, account takeovers, competitive data mining, online fraud, unauthorized vulnerability scans, spam, man-in-the-middle attacks, digital ad fraud, API abuse, application denial of service attacks. So it's our strong belief that this is a huge problem on the internet. In our bad bot report, which is a publication that we provide for the industry every year, in our most recent bad bot report, we made the claim that nearly 20% of web traffic is bad bots, which is an enormous amount of traffic. So good bots are also a large amount of traffic. Good bots are things like search engine crawlers. So obviously, if you want to search for something on Google, Google has to know what the content is on the internet. So they're constantly scraping on the internet. And if you want people to be able to find your website, you want to let those good bots scrape your content. And yet, if your competitors are creating bots to create user accounts on your site or scrape your proprietary information, you want to be able to block them. So that's what we do at Distill. And our data science team has the task of improving and refining and tuning that system and finding more and more bots. So that's a really good opportunity for machine learning. So someone's sitting at a computer making an HTTP request. The HTTP request gets routed through a Distill server, and then we want to route good traffic onto the origin servers, which are going to respond to the HTTP requests with the web content that the user wanted. So in computer user terms, that's someone clicks a link, that sends off a text file saying what content they want back. We get to look at that file and do some things with it before deciding whether or not the customer should respond with the actual web content. So hopefully we can use that to detect malicious bots and then either block them or give them a CAPTCHA, or just some clients for various reasons just want those to be monitored, but we can handle those in a special way. So this is it seems like a prime opportunity for machine learning. We have relatively well-structured data coming in, and a computer has to make a decision extremely quickly as to whether or not it's going to let that traffic through, or whether it's going to handle what we call a violation, so something that is perceived to be malicious. So I'm not going to talk today about sort of the feature generation or machine learning models or any of the science side of this. That's an interesting and very hard problem. I'm not going to go into that now. But so what I want to share is about the engineering feat that we went through last year to modify the system here. So before I go into that, one point of explanation from the technology perspective is that the Distill service acts as a reverse proxy handling these web requests. So if Distill messes up, we essentially stop web traffic being able to go to our client's website. So if you're an online store, you're our client, and we mess up, then people are trying to go to your website and they can't access it. As a result of that, the core systems that run Distill are very sensitive to failures, and they're very resource constrained. And so our machine learning system, at the time being, actually runs as an asynchronous process. So we run the machine learning models outside of these reverse proxy servers. So we get traffic out of the reverse proxy servers, we get log data, and then we process it, and then we send identifiers back to that and say, if you see this identifier again, block the traffic. And so that's just a little bit of context for how we're broadly solving this problem. A few years ago, our data science team, prior to me being a part of the team, built a system for doing this sort of export of the data, running machine learning models, and then sending identifiers back to the clients using an AWS-based system. And what that looked like was we had a system that exported the logs from these reverse proxy servers. These are enriched web logs. And they went into S3. And what our machine learning, first iteration of our machine learning system would do is load those logs from S3 into an EMR cluster on AWS, insert the data into Impala tables, compute aggregate features from those log data, and then stream those features using Hadoop streaming into Python classifiers that were scikit-learn models. And then for users that were flagged, we would send those to a service that would hand them back to our reverse proxy servers that we could then block on. So this was a monumental feat for our early data science team to get this out the door. Yeah, so that's an EMR. All the red is basically all in an EMR cluster. And then we had these pre-trained scikit-learn models inside Hadoop streaming. How well did this work? I'd say pretty good, considering it was written by two PhDs, one a math PhD and an electrical engineering PhD. They were able to ship this, and it operated well in production for a long time. But as time went on, it started to struggle because the log volume grew significantly as we added more customers and as our own customers' websites grew. And the latency for how long it would take to do the classifications was getting longer and longer. And at some point, it got prohibitively long to where it was starting to be ineffective because it would take so long to identify malicious users. There are several other limitations. It was difficult for us, just from an engineering perspective, to update the model. So we would train the models externally and then on an external process, and then have to add them to these EMR images. And it was just very tedious for us to do. It was difficult from a maintenance perspective. Things would fail as if logs had corrupted values, and on the web, you just get insane things that come in web logs. So logs would have corrupted values, and EMR would just spew all kinds of various errors. The two other data scientists on my team were spending a lot of time just doing kind of operational maintenance on this system. There's an inherent latency in this system in that we are essentially batch loading data. So it's something like a micro batch model, but you are not considering data in a streaming paradigm, but you're in these batches. And so you have at least some sort of minimum latency as you wait for the batches to be a sufficient size to run this. And then, as I said, that all that latency was getting longer and longer as the amount of data in our system was growing, and we were just unable to scale it sufficiently with an EMR cluster. And I guess a related point is that it was getting increasingly expensive to run this as we were paying the AWS bills for it. So that all was designed before I joined the team. Our data science team does a lot of our own engineering. We all of us have mostly learned to be software engineers on the job. And we've learned distributed systems and things on the job. And this was a really nice solution in its time. But I came along with a little bit more experience in streaming data systems and engineering these these kind of challenges. And I brought my own perspective and experience into it. And I'm sorry, I skipped ahead. So how well did version 1 work? Well, by the end, it was a little bit of a dumpster fire as we were trying to maintain this thing. So I brought my own experience, and we laid out some parameters that we wanted in a revision of this system. So we wanted to be able to run the same machine learning models, but we wanted to be much faster in terms of the latency between when the original requests come in and when we're able to make classifications based on them. We wanted it to be resilient and largely mean that in the sense of we wanted to spend a lot less time doing maintenance on the system and just allow it to run. We needed it to be scalable in terms of the volume of data that we were putting into it, and hopefully scalable in a cost-effective way. As we add clients, our amount of traffic we're routing through grows more and more. And we also wanted it to be flexible in the sense of the earlier model, or the earlier system was essentially tied to the single model, the single kind of feature generation technique. And so if we wanted to add a separate system that ran in parallel to do other machine learning models, for example, we would have essentially had to duplicate the entire process of spinning up a separate EMR cluster, customizing how we generate the features and all these various things. So we wanted something that would allow us to be more flexible in adding more models in the future. And we wanted it to be independent, and you can think of this in sort of a micro service sort of framework. We wanted this thing to be scalable independently from the rest of the system, deployable independently from the rest of the system. How we solved that was with several changes of technology. So one is we went from using S3, which just allowed us, I mean, it is essentially a poor man's database of all these this structured log data, which was slow and difficult to query and difficult to monitor or to act on in a streaming fashion. So we removed S3 from this process and moved to Kafka. So Kafka is a distributed message queue, so it allows you to have a large volume of data that you can access in a streaming fashion, and you can also access, unlike some queuing systems, you can access Kafka queues from multiple users reading it. So in some sense, the number of consumers of the data is the actual Kafka queue itself doesn't need to know how many people are consuming from it. And one of the big things there is that the consumers monitor their own offset. And so what that means is you're keeping track of where you are in reading this queue. And so as long as you can keep track of it yourself, you can read from it. So we can have multiple processes reading from this Kafka data. So we went through a big undertaking to get our log data off of these reverse proxy servers into Kafka, and that made those logs available in a streaming fashion with a low amount of latency. Similarly, as we were reading from S3, we were effectively reading data from CSV files. CSV files are great in their own way, but as I talked about earlier, you start to deal with corrupted data and issues around that. This was also challenging because these systems are maintained by different teams, and CSV files don't have any sort of type schema, and just a lot of things can go wrong there. So instead of putting effectively CSV rows of data into the Kafka queue, we switched over to using protocol buffers. And protocol buffers are just a serialization format that Google has, similar to other tools, but it allows you to create this language neutral, platform neutral, serialized data structures. So you define the data structures in these text files, protocol buffer files, and then essentially you use those to generate code in whatever language you want to work in to be able to load this serialized data. So when our data is loaded into Kafka, it's converted into a protocol buffer format by a Java process, and then we can read that Kafka data out in a Python process and then use the Python bindings to the protocol buffer to load the exact same data. So we're handing off the data nicely between Java and Python. This is similar to like thrift data. There's some other similar systems. It can be quite nice. The final technology we moved away from was Amazon Elastic MapReduce, where we were running these Impala clusters. So those were expensive. EMR notoriously runs outdated version of various open source things. It just became very cumbersome for us to use. So we moved away from that, and we moved to a tool called StreamParse, which was, in some sense, my big contribution to this project. StreamParse is a Python streaming data platform developed at a startup called Parsely, which I worked at when we were originally developing StreamParse. StreamParse is built on top of Apache Storm, which is a JVM-based tool for distributed streaming computation. StreamParse essentially allows you to take advantage of the multi-lang functionality of Apache Storm without worrying about tons of hassles required to do that in the sort of a native way. So it's analogous maybe to using some high-level tool like Spark or something that does a MapReduce type computation versus writing your own mappers and reducers as people were doing 10 years ago. So I'll show you briefly what StreamParse looks like as to what this allows for. So the Storm model is that you have data coming in some sort of streaming fashion, user-generated events, system-generated events, log events, etc. Storm is agnostic as to how that data gets in, as long as your process can read the data from some sort of streaming platform. And typically, this is going to be data at a very high volume, to where you need multiple processes, or even more likely you want data big enough that where you have multiple computers that are needed to run this. So data enters Storm. Storm processes it in real time. It processes each event, each piece of data individually, versus doing a micro batching like something like Spark streaming. And then it does something with the results of those computations. So typically you'd write it to another data store or something else. In our process, we have the data science team is very fortunate that we get to read data from Kafka, which is very easy to do with a Python library called PyKafka. And we do our machine learning classifications inside of Storm, and then we write the data back to Kafka. So it's relatively simple, and we're not doing a lot of complex database work. And then another team ingests the Kafka output with the machine learning classifications and writes those back to our edge nodes, the reverse proxies. So this is an abstract view of the internals of Storm. And so what Storm gives you is this ability to define a directed graph that is essentially a computational graph. So a spout is going to be a Python process that can read your data, and then it's going to hand that data off to Storm/StreamParse, and StreamParse is going to take it downstream to whatever bolts are subscribing to that data. And a bolt is just a Python process that is going to do some sort of computation and then spit out data in another form. So you can define these arbitrarily complex directed acyclic graphs that do your processing, where each of the orange and yellow, or orange and green components here are just little bits of Python code. And then StreamParse and Storm together are going to run that Python code in a distributed environment. So you can parallelize all of this and scale it up in a distributed environment. And it's also going to handle things for you like fault tolerance. So if you lose one of your nodes and it fails to process some of the data, it's going to automatically try to replay that data on another component that is there. All right, I'm going to hustle through here so I can be done in an amount of time. But this is an example of what a bolt can look like. So it's just a Python class that inherits from a StreamParse bolt. It's going to initialize when it creates itself, and then it's going to call the process function on every piece of data. So in a word count example, the process method is just going to increment your counter for each word. And so you can see more. There's a link in the bottom right corner here. The StreamParse repository has some nice examples of how all this works. So this did work out. This met all of our qualifications. It's very fast. The Storm part of this processes the data in a sub-second latency, which is plenty fast for us. And it's also tunable. Essentially, we can get this thing to go faster by throwing more resources at it. It's a very flexible system in the way that you can add components. So here's a very simple topology that you have a Kafka spout, a classifier bolt, and then the one on the right should say a Kafka bolt, which is going to write the data back to Kafka. But if we wanted to add a second classifier, we could just drop another component into our graph. It doesn't have to know anything about reading or writing from Kafka. It just has to know what the data looks like coming in and be able to produce scores from that. It's very resilient. This is a picture from our Datadog system. The Datadog is a service for monitoring distributed systems. So the graph is showing the rate at which we're reading data over a 5-hour window. And you can see right in the middle, one of our hypervisors that's running the virtual machines that have the Storm processes died. And so it suddenly stops reading. And then without us doing anything, Storm spun up new processes on other virtual machines that were running. And after a little bit of time, it starts reading again, and it recovered itself. It has this big boost where it's reading fast, and then it was able to recover itself. So that was all without any intervention on our part. It's scalable in that this is the Python code defining the topology. So the classifier bolt here, we're saying running in production, run 6 Python processes to do the classification. And we could simply change that to 12 or whatever number we wanted, and then redeploy this thing. And it's going to run more Python processes so it can handle the data at a higher volume. It's extremely easy for us to do. And it's very, very flexible for us. And it also served the independence in that we have this microservice type architecture. It's independently deployable and scalable. It requires the data to be coming into Kafka and someone handling Kafka on the way out, but our process can run independently of any of the other processes handling this. And then it's also gave us independence and a nice way to interface with other teams by using this typed multi-lang serialization using protocol buffers for our data coming in or data coming out. So we can work in Python and essentially not care what the other teams are working in. If I had more time, here's a long list of things. This is a big, complex project. We could talk about testing, tuning, debugging, StreamParse, the speed of protocol buffers in Python, packaging and deploying scikit-learn models, using message pack serialization to speed up Storm, replaying data in Storm, monitoring Storm, securing Kafka with TLS, using these C-based bindings for PyKafka to speed it up, why we didn't use other things like Spark Streaming or Flink, tuning Kafka, maintaining state in StreamParse. there are a lot of topics here that could be discussed. So I turned on the questions here. Someone asked, did you consider other serialization formats, Thrift, Avro, etc.? If so, what did you prefer about protobuf? I was not really a part of the decisions on that. Another engineering team looked into that and they decided on protobuf, and I just went with it. I think there are a lot of neat tools available. Protobuf is great, and it seems like the other ones are great also. We have had issues with the speed of deserializing protobufs in Python is an issue, and figuring out how to compile C-based bindings for protobuf in Python is a big chore. But certainly consider the options out there. Someone else said, what does your hat say on it? It says nothing on it. Well, see, now I just realized that I can hear you guys laugh, so you didn't laugh at any of my other jokes.
Anything else, Dan?
There are a few other questions here I was just looking at. Did you hit an upper limit of documents in Kafka you could recover from? How did you handle that bound? Kafka allows you to save as much data as you want. You just have to decide how many machines you're putting into it. I think we save data in like a 36-hour or 24-hour window, and it's plenty big for us. That works fine. Someone asked about using scikit-learn in an enterprise situation. Did you consider other machine learning packages? Scikit works great if you can run multiple processes to do your computation. It works just fine. And it allows us to move nicely between research and production. And we didn't consider other packages, but I don't see a good reason not to use scikit in this environment. If anyone else, there were several other questions. If you want to email me or reach out to me on Twitter, that'd be great. Thank you, everyone, for hearing me from afar.
Let's give them a big hand, please. You did a great job, Tim. Anyone would like to ask questions? I don't know. What's the time? It's on time. So thank you, Tim. You can ask you offline. You got his Twitter handle, and you can connect with him on LinkedIn, and he'll be more than happy to answer any question. Thanks again, Tim. This is an example how our speakers are passionate about this conference. Nothing can stop them. They got flight canceled. Still, they give the talk. Thank you, Tim. Take care. Bye.
Thank you.